Alright, so this is Markov Chains video 2. So what we'd like to do here is do sort of a long-term behavior experiment, right? See what happens. So let's go back to the original distribution that we had. So the original t that we had was on 0.9, 0.1, 0.05, 0.95. That was our transition matrix. This is the formal name. And we had an initial population distribution of 0.7, 0.3. So let's just look at some calculations. Right, so we know x sub 0. We did x sub 1, but it's worth writing just one more time. I'm going to write 4 decimal digits for each of these. So x2, remember this is t squared times x0. We did this too. This was 5983 and 4017. Suppose we keep going. Suppose we do say x sub 10. This is t to the 10th times x sub 0. So this is 4055 and 0.5945. And then let's do x 100, which is t to the 100 x sub 0. So if we do this, we get 0.3333, 0.6667. Looks like 1/3, 2/3. Let's do one more. If we do 1,000, we get exactly the same thing. Now, there's some approximation going on here, of course. I did this in MATLAB. But it looks like the following. We go, So two things seem fairly clear. One is that the limit as n goes to infinity of t to the n x sub 0 is 1/3, 2/3. Right, that's just simple data for this particular x sub 0. But it also suggests that if I apply t to 1/3, 2/3, maybe it doesn't change. So maybe it's heading towards that distribution, but it's heading towards that distribution, and if it were at that distribution, right, perhaps it wouldn't change. So the second of these, this is easy to check. Right? If you literally take this matrix, if you just take it, this guy right here, and you multiply times 1/3, 2/3. I'm not going to write down the calculation, but you will get 1/3, 2/3. Right, so it is evidently clear that that the second one will absolutely work. Right? Now, the first one, like, it certainly looks true from the data, but it leads to another question, right? We might say, like, what if I had started with a different distribution, not 0.7, 0.3? So the first, let's say this way, the first makes us think. Right, what if x sub 0 was something else? So we could try it, right? So let's try maybe x sub 0. Let's make it really lopsided, right? Let's make it 0.05, 0.95. So let's put almost everybody in state 2 to begin with. Right? So then what happens is if you start calculating this, right? If we do x sub 1, which is t x sub 0, this is 0.0925 and 0.9075. And if we go to x, let's say x1000, x100, I won't show all the intermediate stages, of course. Let's do x100 first. What we see is we get the same values. Same for 1,000. So it stands, it looks like, potentially, this is not a proof, but it looks like in the long term, it's heading towards 1/3, 2/3. So this should sort of really interest us, right? So our moment is like, wow. It looks like it always, I mean, this is 2 data points, let's be clear. So always is a bit, it's sort of a bit, I don't know, obnoxious perhaps, but it looks like it always heads towards 1/3, 2/3. All right, could that be the case? So we're going to answer this question, and I'm going to do it within the context of like the formal description of what's going on here. So let me clear the screen, and then we're going to give formal definitions for these matrices, for these vectors, for what it means to have a limiting vector like this. And then there's going to be a theorem that we're going to give. We're not going to prove it because it's fairly intense, but at least we can state it, and then we can rely upon it with our data. So we'll say 2. Formal stuff. So first definition. So our vectors that we had always added to 1 because we thought of them as distributions of probabilities, or distributions of populations rather. So the formal definition of such a vector is called a probability vector. Adds to 1, we can think of it as the chances that things go from states to states, right? So a probability vector, maybe a distribution vector might be a better word for us, but probability vector is the right word. So this is a vector whose entries add to 1. So all our distributions are these types of things. So a transition matrix is sometimes also called a stochastic matrix. But transition matrix is a better phrase for us. This is a matrix in which each column adds to 1, and that matrix tells us how populations shift. So this is a matrix whose columns each add to 1. You could say that each column is a probability vector if you like, but we can say it adds to 1. And then we can say, for example, that column J tells us how the population of state J behaves. We'll say at the end of each iteration. All right, C. So now we're gonna have a definition for like the special vector which is held fixed, like the 1/3, 2/3. So this is called a steady state vector. So a probability vector has to be a probability vector to start with, is a steady state vector. So we'll say probability vector X is a steady state vector if Tx equals X. In other words, it's not changed by the transition matrix. Now notice this is a familiar equation, right? So note what this means is this is the same as Tx equals 1x, which is the same as saying that X is an eigenvector with eigenvalue 1. So saying the same as X is an eigenvector corresponding to eigenvalue lambda equals 1. Now, next definition. This is going to be a bit obscure because we haven't sort of really run into it yet, but we need it in order to talk about the big theorem that comes next. So, a regular transition matrix. This is an odd definition. A regular transition matrix is a transition matrix which has the following property, that you can find a power to raise it to in which all of the entries are 0. So this is a transition matrix T such that there is some n in the naturals, like some n, let's say positive integer with t to the n all non-zero. In other words, not a single zero in the entire of Tn. Now we have this big theorem. So the theorem says the following, right? If you have a regular transition matrix, and if it has, or then it has lambda equals 1 as an eigenvalue, and then there is a unique steady state eigenvector. So if T is a regular transition matrix, then two things are true. One is lambda equals 1 is an eigenvalue, and there is a unique steady state vector, which will typically denote x sub star. Now, it's not just a unique steady state vector, it also has the property, which has the property that for any x sub 0, the limit as n goes to infinity of t to the n x sub 0 equals x sub star. In other words, it doesn't matter what state you start with, you will end up at x sub star. So no matter the starting state, you limit to x star. And of course, that can be found by finding the eigenvector that corresponds to lambda equals 0. Right? So in this case, we find it by finding, we'll do this, finding the eigenvector corresponding to lambda equals 1. Now, there's a little division that needs to happen when we get there, but that's okay. So let me clear the screen. I want to give a corollary to this theorem. We're not proving the theorem. The scope of the proof of the theorem is beyond the scope of the course. But I want to give a corollary to the theorem, give some additional facts, and then just write down an example. Look at an example of the full theory. So F, corollary. This is corollary to the theorem. So corollary to the theorem is that if T is regular, then there's another sort of slick way. If you just need an approximation for the vector, then let me say it this way. If we take, say, if we take t to the n, the limit as n goes to infinity of t to the n, right? Every column will be x star. So the proof of this is actually pretty easy. So the proof of this is as follows, because we can prove this. Right, so for each e sub I, this is a, remember e sub I, this is a basis vector which has a 1 in the ith position. So for each e sub I, so we know the limit as n goes to infinity of t to the n e sub I will be x star. So it follows from there, if we take the limit, if we put all these basis vectors together, when you multiply a matrix times a matrix, the formal definition of a matrix times a matrix is you multiply the matrix by each column. So if you do this, you will get a matrix all of x stars. But then on the left, that's just the identity matrix, the matrix of the e's. and that's the result, QED. Now, a couple of following facts. We'll see this in practice if it's a bit confusing. Okay. So the first fact is the theorem tells us that if the transition matrix is regular, the results will hold. But if the transition matrix is not regular, we just don't know. The results may still hold. Right, it's not an if and only if theorem. And the fact two, which is sort of more of a thing to be careful about, is that if you use something like MATLAB to find the eigenvector, right? So if we use, say, MATLAB is a good example, but this is almost true for every single software package to find the eigenvector. Right? Typically, it will not give you a vector whose entries add to 1. It will give you a unit vector. So in order to make the entries add up to 1, you just divide by the sum of the entries. So remember, a unit vector has magnitude 1, which is not the same as having sum 1. Right? So if we divide by the sum of the entries, this is to make it a probability vector. So let me pause there, clear the screen, and then I just want to work through an example. I just want to give a matrix, talk about what it means for it to be regular, give like example by example, and then sort of see what we can say about the steady state. So example. So consider this transition matrix. So we'll go, this is the second one that we ever saw. This is the first one that had 3 entries. Okay. So remember, when it means to be regular, it means there's a power you can raise it to so that the matrix is all non-zero. So it's t to the 1 is already non-zero. So t is regular. So therefore, the theorem tells us that there is a steady state vector, right? So if we go into MATLAB, for example, and say if we find the eigen stuff, the eigenpairs, so we find the eigenvalue 1. Now, MATLAB will tell us, what I did this in MATLAB. MATLAB gives the eigenvector. This is approximately, I'm going to copy all the digits that I wrote in the book. So this is a unit vector, right? In other words, this has magnitude 1. The sum of these is not 1. Right? You can see that, right? You can add those entries up. You don't even have to add them up precisely in your head. You can see that you're going to get more than 1. So to get a probability vector, remember that multiples of eigenvectors are eigenvectors. So if we divide by the sum, we will get our x star. If you do this, we get 0.58. I'm going to write all 6 digits, just the same as the book, but you get the idea. These do add up to 1. So this tells us the long-term behavior. All right, so the long-term behavior if you like it in terms of percentages, you could be like, oh, 58.1397% is in state 1. Right? It'll tend to settle there, in other words. 25.5815% in state 2, and 16.2791% in S3, right? So in other words, it tends towards that, right? It limits towards that. Limits to this distribution, no matter how it starts. And so it limits there, and if it were there, it would never leave there. It would stay there, right? And so moreover, this other note, just take a note, if I had done like t to the 1000, if you do this, right, what you'll find is you'll get, now you may not get the exact right numbers because this is just, 1000 is not a particularly big number. You'll get this. And then you got the same thing here again and again and again. These are horizontal dot dots. So it's the same here and the same here. And so it's almost the same as X star, right? It's not exactly the same because t to the 1000 is not really, really, really big. Right? So notice the columns are approximately X star. Right? They limit to X star as t to the n gets bigger. So I'm going to stop there for now. That sort of helps us see the theory, helps us to know what to do with a specific example. I'm going to do one other video because there's more that we can do when we're looking at transition matrices, right? So we can look at these transition matrices and we can get more information out of them. We can analyze them in more detail, especially with these transition diagrams that we drew. And we can understand sort of what's happening to the populations a little bit more. So let me stop there and I'll put that in the third video.